here's a very nice application of the law of total expectation to waiting times. So remember, we computed the expected waiting time using that complicated sum, which comes directly from the definition of the expected value. So we have this complicated sum. We computed the expected waiting time. So I'm going to show you, a way of analyzing such processes that go on, can potentially go on forever. Okay. And we will think of the experiment as, okay, you start, okay, and you can either get a success or a failure. So if you get a success, okay, with probability P, you're done. Okay, you're done. Okay, you got one success. Okay? Or you can fail. You can fail with probability 1 minus P. Okay, in which case, you restart. Okay, because you try again. And so basically you're at the beginning of the experiment, except that you've used up one trial. Okay, so we're gonna, we're interested in the waiting time. So we're interested in the expected waiting time. Okay, and we're going to use the law of total expectation. The law of total expectation. Okay, so let's work it out, and you'll see how, there's not going to be any infinite summation or anything. It's just going to drop out effortlessly. So the expected, so that x equals the waiting time. So the expected waiting time is exactly the expected value of x, and we'll break it down into two cases. Now, you can use total expectation with more than two cases, but most commonly we break it down into two cases. So this is the expected waiting time if you succeed, okay, times the probability of success. Okay, so case one is you succeeded on your trial, okay, plus the expected waiting time given that you failed times the probability of failure. And why failed? Because the complement of success, so you didn't succeed is basically you failed. Okay. Now let's see if we can put numbers onto these. The probability that you succeed is P. The probability that you fail is 1 minus P. Okay. Now, the expected waiting time if you succeed, well, you're done. It's just one step. So this is just 1. Okay. What's the expected waiting time if you fail? This is the interesting guy. Okay. Well, if you fail, you're back to the restart. You're restarted. So you wait. So you've used up one step. So you have the wait is equal to one step plus, okay, you've used up your one step plus now you have to restart. So you expect to wait. Your expected waiting time is exactly the expected waiting time at the beginning. So 1 plus the expected value of x. Okay. Now, you have to sit down and think about what's going on here. So if you fail, you used up one trial and you're back to the beginning. So your expected waiting time is the one trial you've used up plus how long you expect to wait, from the beginning, from a restart. Okay. But if you restart, how long you expect to wait is exactly the guy that we're trying to compute, the expected wait from the beginning. Okay. So this is equal to P plus 1 plus the expected value of x times 1 minus P. So let me collect terms. This is P plus 1 minus P, P plus 1 minus P, okay, plus the expected value of x times 1 minus P. Okay. So this is 1 plus the expected value of x times 1 minus P. Let me take this now this is what typically happens when you consider these processes that can restart. So you have the expected value of x we haven't computed it. We've given an equation it must satisfy. This expected value of x must equal this 1 plus the expected value of x times 1 minus P. If we take this to the other side, we get that the expected value of x, one of them, minus 1 minus P of them, is equal to 1. So 1 minus P, this is just P. Okay, the 1 minus 1 cancels and the minus times minus P is plus P. So P times the expected value of x is equal to 1. This means that the expected value of x is equal to 1 over P. Boom! We already derived this, but now it's very simple algebra. And, I went through it very slowly because probably this is the first time you've seen this. Okay? But, now you can imagine that once you become an expert at using the law of total expectation, these things are going to become secondhand. They're just going to be, trivial for you. Okay? So get good at the law of total expectation, the law of total probability. They make computing expectations and probabilities. They can make computing expectations and probabilities much easier. Okay. All right. So, if you're waiting for a girl, then and the probability of a girl is 1/2, so success is the girl, then your expected time, wait time till success is 2 children, just like we had before, 1/p. And you might imagine, what if I'm waiting for 2 girls? Okay, what's my expected wait? So I get the first girl, now I'm waiting for a second girl. You might guess that it's going to be twice the expected wait for 1 girl. Okay. And what if I'm waiting for 3 girls? You might guess that it's 3 times the expected wait for 1 girl. Okay. And we could guess that the expected wait to k successes is just k times the expected wait for 1 success. Okay, it's just k times 1/p, or k over p. That's a guess. Okay, in case any of you are wondering, well, what if I'm waiting for 5 girls? How many children do I need to have? Well, it sounds like you're going to have 10 children, or you'll expect to have 10 children. Or if you repeated that experiment many times. Now, I don't know who's going to repeat an experiment to have kids until they have 5 girls many times. But if you did, you would expect on average that 10 kids are needed in order to get 5 girls. Okay, so you have a complex experiment. You have a complex outcome. The random variable summarizes the measurement. Okay, so you summarize the measurement in a random variable, and the random variable has a probability distribution function associated with it, corresponding to the probabilities of each possible value for the measurement. And then we further summarized to the expected value. So we've condensed the whole experiment to one number now, which is what do you expect to happen, okay, with a grain of salt, if you repeated this experiment many, many times with respect to the quantity that you are interested in, the measurement. Okay. So if you repeat it many, many times and then made your measurement on average, what would your measurement be? It's the expected value. And now we did some examples of computing expected values, and we introduced some tools. The law of total expectation is a power tool. Okay? And expectation is so important. We're going to spend another lecture on it next time. So see you then.